Okay, so on this worksheet, the answers are the numbers 0 through 9. None of the answers are going to be repeated, so we just need to be watching for that. On the first one, we're supposed to find a right-sided limit for f of x. And so because I'm looking for a right-sided limit, I need to choose the branch of the piecewise function for the right side of the borderline, and the borderline is 3, and so I'm going to choose the part for the graph that is greater than 3, so I'm going to choose this section. And so what that means is I need to put in 3 into that part of the equation, and I can do direct substitution for that one because the function is continuous at that spot, even though it's a piecewise. So the branch of the piecewise function is continuous at that spot, or at least it would be. And I'm just looking at a right-sided limit. I don't really actually care about whether I can use the test correctly or not. I just need to look at the right-sided limit. So that's exactly what this is going to do. So I just need to put 3 in for x. And so negative 3 times 3 is 9, plus 15 is 6. For the second one, we're supposed to do a two-sided limit. So because it doesn't have a plus or a minus above the 2, we're supposed to look at what's happening at 2. And so I can look at my left-sided limit and see that the graph is approaching this value of 3. And from the right side, it looks like it's doing the same thing. It's approaching the value 3. And so since the left and right-sided limits match, we can write 3 as our answer. For the next one, the graphical method is totally fine here, but what I will say is that you can rewrite this as 8 over 2 times the limit as x approaches 0 of sine of x over x, and we've seen that graph of sine of x over x a bunch of times so far this week, and so we know that sine of x over x approaches 1 at 0, and so this whole component right here, just this part, is going to 1. And so if we've got 8 over 2, well, I'm just going to write 4, right? 4 times 1, that gives me 4. Okay, next one. We're supposed to find the a that allows the function to have a limit that exists at 3. And so what that means is we're trying to make sure that the left and right-sided limits match. And really what it is, too, is can we find a value a that makes this function continuous? Because if we can make it continuous, then that means that it's the limit will exist. So ultimately what we're doing is we're saying, okay, before 3, it's this. After 3, it's this. Or 3 and later it's that. And so we need to make those match. So we're going to set up 4x minus a equal to x squared plus ax minus 1. Then we just need to set up the equation, solve the equation, figure out what happens after that. The other thing is, because we're working at what happens at x equals 3, we can put 3 in here for x, and here for x, and here for x. And so we'll get 12 minus a equals 9 plus 3a minus 1. And then we just do algebra. I guess I'll add a to both sides. And then right here I've got 9 minus 1, and so that's 8. So I'm going to subtract 8 from both sides. And I get 4 equals 4a. So then a is 1. Okay, the next one is one that I think we're going to need to do direct substitution for. At least we should try that. So we'll plug in the negative 2 for all the x's. And when you do that, you end up with one of those indeterminate forms. You're going to end up with 0 over 0. And so when we have 0 over 0, that means that we have a indeterminate form, and that means that the 0 over 0 means that we're going to have a whole. And so when we have that, then we need to factor the numerator, factor the denominator, look for something common to cancel. The top factors as x minus 8, x plus 2. So I'm hoping for an x plus 2 in the denominator, and I get one, x times x plus 2. And so therefore, this term will cancel with this term, and so we're left with the limit as x approaches -2 of x minus 8 over x, and now we can do direct substitution again to try that. So we end up with, if you put in -2, you get -10 divided by -2, which is just 5. Okay, the next question is kind of similar. It's asking where on the graph does the limit not exist? And so this would be a situation where we would be saying, okay, one of the discontinuities, possible discontinuities, would be a hole. One of them might be an asymptote. So we need to take a look at h of x and see what happens. Maybe we can factor it first and then look for something common to pull out. So the top factors as x minus 4 times x plus 3. And then the bottom factors as x minus 4, and then x minus 9. So I can see that I've got this x minus 4 twice, and so I can see that I have a hole at x equals 4. So that means that's not a discontinuity. Or sorry, that's not a place where the limit doesn't exist. It's a hole, but the limit exists there because the left and right side limits will match. The place where the graph does not have a limit is where the denominator is 0 that's left, and so x equals 9 is our discontinuity. This one you might be tempted to just kind of almost treat it like a direct substitution problem, but we need to be really careful here because even though the function is valued at 3 for x equals -2, you can look at the left and right sided limits and notice that these are not going to 3. So these are actually going to 0. The limit is going to 0 even though the value of the function is at 3. So that's confusing, that's sort of surprising, but what we would expect as we are approaching -2, the y values are going towards 0. Okay, the next one is kind of a hard one because there's a lot of canceling that we're going to have to do and a little bit of careful algebra. Make sure you're foiling and not forgetting about the b terms when you're doing that. This is going to be equal to limit as h approaches 0 of 49 plus 14h plus h squared. So that's just where I got this part. Remember, don't forget to FOIL there. Okay, and then we've got minus 42 minus 6h. So that's just this portion right there. Okay, and then plus 2. And then all of that minus 9. And it's all over h. Okay. At this point, the parentheses that I drew are not really doing anything, so I'm going to just erase them because they're just confusing at this point. I'm just looking for like terms here that I can combine, and so I see 49 and 42 and 2 and 9, and all those add up to just 0, so they go away. They're not relevant anymore. And then I have the 14h and the 6h, so we're going to add those and get 8h, and then we've got that plus h squared still too. It's really important that you keep the limit notation, and then we just have to factor. So we'll pull out a common h. And then these two cancel. So we've got h and h, those cancel. Now I can plug in 0 for h, so I'll get the limit as h approaches 0 of 8 plus h. We plug in 0 for h and we get 8. On this graph here, we're looking for all the places where the limit does not exist. So we're looking for places where the left and right side limits don't agree. And even the discontinuities, so these, like this one right here and this one right here, those don't count. Those are not relevant there because even though they're not defined, the function's not defined at that spot, the limit still exists. So just the green circles, and so that means that it's twice. So 2. Okay, at this point we can probably do process of elimination and find out that it's 7, but remember that this is one of those graphs that looks like this, where you got one of these and one of these, right? But we've been translated right 5 units, so from the right we've got, this is now at x equals 5 right here, and then the 7 is stretching the whole thing up, so we've got 7 and negative 7. So from the right side, the limit is approaching 7. There's our answers.